own pressure. Oxygen will have its own pressure. And I'll say, we don't care that the other gases are there, I have my own pressure. Okay? So if we were to look at nitrogen, out of that 760 millimeters, nitrogen's pressure is somewhere around 597-ish millimeters of mercury. Out of that pressure, the pressure of nitrogen makes up that number. Okay? So most of the gas in the atmosphere comes from nitrogen. Oxygen is about 158 millimeters of mercury. Water measures about 3.0. Carbon dioxide, 0.3. And then others is like a 0.5%. So if we add it up, it comes close to that 700 millimeters of mercury. So each gas has its own pressure. It doesn't care about the other gases. So it says, all right, I have my own pressure, fine. I need to do what I need to do. So when the atmospheric pressure changes, obviously the pressures of each of the gases will change. Okay? But when we talk about an atmospheric pressure, just know it's made up of a bunch of different gases, and each gas has its own pressure. The third gas law is called Henry's law. And Henry's law states that the quantity of a gas that will dissolve in a liquid, okay, the quantity of a gas that will dissolve in a liquid is proportional to the partial pressure of the gas and its solubility coefficient. Let me repeat it one more time. Henry's law states that the quantity of a gas that will dissolve in a liquid is proportional to the partial pressure of the gas and its solubility coefficient. Now, what does all that mean? Okay? It means that in certain circumstances, I'm going to use the soda bottle as an example. Okay? What happens when you open up a bottle of soda? You hear a shh, right? You hear a noise. Okay? Okay? So when you open up, what's happening is you're decreasing the pressure and releasing a gas. Okay? So nitrogen gas can easily be released in a condition called decompression sickness. For those that are either familiar with scuba diving or know about it, you're going down deep into the water. So what's happening to the pressure? Okay, it's becoming greater and greater on your body, right? Now go back a second. You just had a bottle of soda. Do you just open it up right away, or do you kind of like turn the cap a little bit at a time, let some gas out? Because what's going to happen if you totally take the cap off? You're going to get a shower of soda, right? So the same thing. You want to, if you're a scuba diver, okay, you have to be careful of a condition called decompression sickness, which is known as bends. Okay, so you've gone deep down in the ocean. There's a lot of pressure on your body. You need to rise to the surface very slowly, because just like the soda bottle, if you rise too quickly or take the cap off of the soda too quickly, gas is going to escape too quickly, but you're going to get severe cramping, okay, to your body. Okay, and that's why we call the bends, because scuba divers would keel over and bend over in agony and in pain. So you have to rise to the surface very slowly to compensate for the change in pressure from going deep sea to the surface. Same thing with the soda bottle, okay? You're opening it up, you gotta open it nice and slow because you have to make sure that the pressure, the amount of gas that gets released, levels off, otherwise you're gonna get a shower of soda, okay? And that's what Henry's law is. So when you think of Henry's law, think of a soda bottle and think of deep sea diving, okay? Now, scuba divers that get this decompression sickness, they need to go into hyperbaric chambers in order to combat the bends that they get from rising to the surface very quickly. So what happens is that causes oxygen to dissolve into the blood to treat the anaerobic bacteria that can happen to occur in your body, which may cause tetanus and or gangrene as a possible side effect of the bends. Okay? So let's look for a second, keeping those gas laws in mind, at this next slide. And this next slide shows us, once again, pressures of oxygen, pressures of carbon dioxide. Okay? As we're breathing in oxygen, you can see O2 is inhaled. So it means it's coming into our body, we've taken a breath in. And CO2 is exhaled. Okay? We've expelled it. Okay? And that's happening at the alveoli. So the alveoli is that small little grape-like structure inside our lungs where we're going to get gas exchange. So as we breathe in, right, we're breathing in oxygen. As we breathe out, we're breathing out our CO2. Remember early on, one of the first slides, how in close proximity the capillaries were to the alveoli? We're looking right on top. Everybody remember that picture? Okay. Well, here's the pulmonary capillaries. Okay. It's right near the alveoli. We breathe in. Okay. If you look at the lungs, anybody remember what type of cells we find in alveoli? It's a single layer of flat cells. Okay? It's a simple squamous epithelium. So think back, what was a function of something that was a single layer and very flat? Diffusion, right? This is why the lungs have simple squamous epithelium, because in diffusion, things can come in and out very readily, right? A passive process doesn't require much what? Energy. Doesn't require much ATP at all. Okay? Because it's a passive process. So as you breathe in, okay, and due to the different changes in pressure, okay, think back to that slide as we breathed in. Okay, what law was that? Pressure and volume. Boyle's law. Okay. Oxygen made it in. Okay, to the pulmonary. Yep.
Right, so Boyle's law is occurring where?
Well, Boyle's law is occurring with the changes in pressure. Okay. So we get oxygen into the bloodstream. Okay. Now from the lungs, how does blood get back to the heart? Pulmonary veins, right? Lung, capillary, pulmonary vein. Okay? To your left atrium, right? From the left atrium, we could go through the mitral valve, into the left ventricle, then through the aortic valve, into the aorta, into your systemic circulation. Okay? Arteries bring blood to what? Tissues, right? And organs, right? Your systemic circulation. So we've reached our destination. Okay? Here are the cells of your little toe. blood leaves your systemic circulation, gets eventually into your systemic capillaries, right? What happens now to the oxygen? It leaves the blood, gets into the tissues, right? Tissues gobble up that oxygen, use it up, produce what? Waste called carbon dioxide, right? And eventually gets back into the capillary bed, venules and veins, inferior vena cava, right? Back to the right atrium. And then eventually, when you get into your right ventricle, you go through your pulmonary what? Pulmonary trunk to your what? Good. Pulmonary arteries to your lungs. Okay? So with the changes in pressure, okay, your carbon dioxide and your oxygen can now exit the lungs or get back in the lungs, travel through your bloodstream, circulate around, and eventually, once again, feed a tissue, feed an organ, feed a gland. Then the carbon dioxide that's produced as waste goes back into the blood where it can get back to the heart and to eventually to the lungs for you to expel it from your body. And that can happen because oxygen has its own pressure. So you're going to go through pressure changes. Look what's happening to the pressure of oxygen, okay? Right here. Pressure of oxygen. The P stands for pressure. Okay? So in the atmosphere, PO2 is what? 159. We now breathe it in. Look what's happening to the pressure of the oxygen. Right? It's going down, right? See that? As we get to our destination, the pressure of the oxygen is starting to decrease. Look at our PCO2. Okay? We're breathing in oxygen, so therefore the pressure of our carbon dioxide should be lower. But then as it travels in our bloodstream, it eventually starts to do what? Go up, right? Because once we use up oxygen, what happens to the amount of carbon dioxide? That starts to go up, so the pressure has to go up. Right? So if everybody understand what's going on? Now, it's not as simple as you breathe in oxygen and you breathe out carbon dioxide. Okay? Those two gases don't just flow through your bloodstream as oxygen and carbon dioxide. Right? Not that simple. Oxygen has to bind to hemoglobin. Right? Oxygen has to bind to hemoglobin. Hemoglobin is found inside your red blood cells. Right? So, in your red blood cells, you have this hemoglobin. Okay? It also helps give the color to your cells. So the oxygen has to actually bind to it. There's only a certain amount of hemoglobin inside a red blood cell. So each red blood cell that you have can become saturated or unsaturated with oxygen, or they can be saturated or unsaturated with carbon dioxide. So, as an example, use purple. Here's our red blood cell. Let's say our red blood cell has 4 hemoglobins in it. Okay? If each hemoglobin can bind an oxygen, we would say that that red blood cell is 100% saturated with oxygen. Everybody see that? Understand that? So just a typical red blood cell has 4 hemoglobin proteins in it, and each one can bind an oxygen molecule. If all 4 of them are bound to an oxygen molecule, it's 100% saturated with oxygen, right? So all of them are bound, right? Let's say we take away one of the oxygen molecules. What would our saturation be now? What percent? About 75%, right? Because now 3 out of 4, 3/4, 75%. We take another one away, 50%, 25%, and then it's not saturated at all, okay? So in your body, right, this should actually read O2. So make a note that this has to say transport of O2, not CO2. Okay? Once again, another typo by our lovely publisher. So the transport of oxygen, 98%, not more, of your oxygen in your body has to bind to hemoglobin in your red blood cells.
So 98, not 98.
About 98%. Okay? So the majority, if not more than the majority, of your oxygen has to bind to hemoglobin inside a red blood cell in order to travel in your bloodstream. Right? It cannot travel very readily as free oxygen. It has to bind to something, and it binds to the hemoglobin inside your red blood cells. Okay? There is a very, very small percent of your oxygen that's dissolved in your blood plasma. And remember when we centrifuge the blood, it's separated into the plasma and the formed elements. Okay? So it's in that plasma where you'll find just a small amount of oxygen. Okay? But it has to, in order to travel through the bloodstream. Okay? Oxygen has to bind to hemoglobin. So we get this oxyhemoglobin combination. Now once oxygen is used up by tissues, okay? So once again, we took in oxygen left the alveoli, made its way to the bloodstream. So that means even though the capillaries are pretty much right on top of the alveoli, there's a microscopic space between those two structures, right? That's your interstitial fluid. So for a minute, oxygen has to travel from an alveoli through your interstitial fluid into your capillary. Okay, once in the capillary, it has to make its way into a red blood cell, bind to hemoglobin, and now the red blood cells can travel throughout your body, make their way to tissue cells. Okay? Once they make their way to tissue cells, they have to dislodge themselves from the hemoglobin, okay? Because now that oxygen has to get into the tissue. So it means it has to unbind from hemoglobin, leave the capillary, go through the interstitial fluid into your tissues. Your tissues will use it up. And producing what now? Waste, which is what? CO2. Now, CO2, okay, once again, goes through your interstitial fluid into the blood. But CO2 has its own things that it has to bind to. Okay? CO2, if we look at the chart up there, okay, 70% of your CO2 that's produced in your body gets converted into what we call bicarbonate ions. Okay? Gets converted to bicarbonate ions. That's what HCO3 negative is. It's bicarbonate ions. 70% of your CO2 gets converted to bicarbonate ions. The 70% of your carbon dioxide gets converted to bicarbonate ions, and HCO3 negative is the chemical formula for bicarbonate ions. Okay? 23% of your carbon dioxide will bind to hemoglobin. Once again, the hemoglobin's in your red blood cells. And then you will have a small percent, okay, what's left over, about 7% gets dissolved into that plasma. Okay? So where oxygen has to bind to hemoglobin, form an oxyhemoglobin, okay? Carbon dioxide mainly travels as bicarbonate ions. I'm just going to show you a slide that you really do not have to memorize at all. Okay? Okay? At all. But I just wanted to show you so you get an understanding. Okay? You don't have to memorize, you don't have to think about anything of this slide. Just listen. Okay? This picture here is the exchange of your oxygen and carbon dioxide in your pulmonary capillaries. Pulmonary capillaries are in what circulation? Your pulmonary circulation, right? Okay? That is your external respiration. Think back, didn't we read you the definition of external respiration and what it involved? So, in external respiration, okay, here's an alveolus. Okay, we're intaking oxygen, we're expelling carbon dioxide. Basic, easy, right? Now, in external respiration, okay, here's the capillary wall. Remember, a capillary is just endothelial cells lined end to end, but there are spaces between them. So oxygen and carbon dioxide can diffuse through. So right here, you can have the diffusion through. So oxygen is coming in, okay? It has to bind to hemoglobin, okay? So here's how it chemically converts into an oxyhemoglobin. What happens? And at the same time, carbon dioxide, which was a bicarbonate ion, gets converted back to CO2 so it can now be expelled from your body. And what happens? So there's a lot of chemical reactions that have to occur. Okay? Once again, it's not just that easy. Breathe in, breathe out. Before you breathe in and your oxygen circulates, there has to be some chemical reactions that occur. Before you breathe out, you actually expel out the carbon dioxide. There has to be chemical reactions for carbon dioxide to get converted back from bicarbonate ions to CO2 for you to bring it into your lung fields to get that out of your body. Okay? Internal respiration. Once again, tissue cells, red blood cells. Here we got a systemic capillary. So once again, here's your systemic circulation. Okay? Once again, as CO2, okay, it has to get converted to bicarbonate ions. Okay? Oxygen being brought into tissue cells. Okay? First it starts as an oxyhemoglobin, then once it reaches the tissue cell, it's got to cross, okay, a systemic capillary wall, right? Because it's not bringing blood to the tissue. Okay? So now the oxygen has to unbind, cross that systemic capillary into the tissue. It's used up, produces CO2. CO2, okay, gets brought back primarily as bicarbonate ions inside your red blood cell. Some of it as carbon dioxide, and then some in your blood plasma. So a lot of different things have to happen when you take that breath in and when you take that breath out. So now, every time you breathe, I want you to think of what pressure has changed. What's happening to the carbon dioxide? What's happening to the oxygen? How are things circulating through my body? Okay? We take for granted that we just breathe in and out, our lungs expand and constrict, our heart just beats. But we don't realize that it's more intense than just that. Right? I just wanted to show you this slide because it is an extremely simple procedure.
How long does this whole process take? Is it a breath in, a breath out, or is it long?
I mean, it's in fractions of seconds. Okay? Because your blood is constantly circulating. Okay? And we're constantly breathing out our carbon dioxide, breathing in new oxygen. Okay? So as quick as it takes red blood cells to go from point A to point B, and eventually let out their oxygen and get carbon dioxide back in for it to. So pretty much, every minute, okay, because remember we talked about our cardiac output, okay, how much is circulating through our body each minute. Okay, remember we came up with that one example where your entire blood volume can circulate through your body each minute. So within a minute, your blood's circulating, so eventually think of a red blood cell. So in about a minute, you've got exchange of oxygen and carbon dioxide. So that red blood cell from start to finish. All right, let's take a 15-minute break because I'm tired of talking. Yeah. Change the pressure because what's happening as you go up high, the pressure drops. And what's happening is that air probably out of his blood too fast, and his lungs too fast, and he didn't equal out. You normally don't hear of that happening. Those are probably just extreme cases, and everybody is different. Right, everybody's different. But, did he literally leave the water and go in an airplane? Like, yeah, I mean, it's almost like, you travel from New York and then you go on a hike. Like, not even a hike. Like, when I went out to the Grand Canyon, obviously that's 4,000 feet up compared to sea level where the air is a lot thinner. So your body doesn't need time to adjust. So you can get fatigued really quickly, you can get lightheaded very quickly. I had forgotten my car keys or something in my car, so I ran back to the car and whatever, and I felt like I ran a marathon. So it could have just been something where his body was not accustomed yet. It just, even though it was a day, and he came up from deep sleep slowly, it's just that his body just didn't adapt to the changes in his pressure. Well, that's a whole different thing, because I won't go in the water. If I can't see my toes, I am not going in the water. Not that I'm scared of the water, I'm scared of what's in the water.
Yeah, if you can't
Like
see
a pool?
down. No, if you
No,
can't see
if I can't see my toes in the ocean, I am not going in the water. It has nothing to do with clean, it has to do with in the water. Exactly. And vermin, whatever that's in there. So if I cannot see my toes, okay, which is only 5 feet down, I am not going in that water. Period. End of story. Because I want to see what's swimming between my legs and toes.
I want to go.
Like, I wouldn't mind going scuba diving. And once again, as long as I knew there were no sharks or anything.
Because of that pressure thing that you talked about that happening, I didn't go
Deep sea diving, yeah.
I didn't do anything because I got scared because I was like, oh, we first have to take it for training with these.
It's important, yes.
But I didn't know that at that time. They just told me, they told me that, and my mom was having this emotions, and I was like, oh, no, we're not gonna go do anything.
But part of your training of scuba diving, you can go through it. You need to travel up slowly. like the deeper you go down, if you go
Yeah,
down,
but
if you go down 20 feet, you're not gonna, feel this much, because you've been in a pool and you've gone
No, you
10
could
feet
feel
down.
it in a pool. When you go all the way down,
No, but
you
I'm
feel
saying,
the pressure change.
but you've gone, like, in a deep end of a pool, that's like 10 feet down,
Mhm.
and you come up pretty quickly, it's not gonna happen then, you've gotta go, even, a little bit deeper than, 10 feet down. It could be like 50 feet, 100 feet, and you're gonna feel it, like you said, you go into a pool, you go all the way to the bottom, you can feel the pressure being, pushed on your body.
Yeah, that's scary. That's not everything. And now you're telling me all these things that can happen. I'm like, okay, go.
Because can it happen? Yes, but will it happen? If you know safety, then it won't happen. People school that all the time.
No, she takes 45 minutes.
I work in the hospital, so
Yeah.
I'll take it out. What do you mean? No. Oh my God. Huh? No. Oh, look, you some of the candy? Oh, this candy? No, I took this from doctor's office actually. And yeah, I have no good thing.
Lucy.
Yeah, Twizzlers, everything. I'm like, yeah, I'm not. My child, 17, trick or treating. Right. They do. Yeah, she went to a party.
What's up, Donna?
Oh, you got shit.
Having fun yet? You having fun yet?
What's up with that?
What lab?
You have to, no, you're not.
We put them up online.
Look at him, he's out here, right?
I did not even take a glance at them.
Come on!
Maybe we'll lose them all and get
So
them.
we gotta wait like 2 weeks?
No, you'll have them back no later than this Tuesday.
Okay.
Will you post them if they're done before that?
Yeah.
I keep checking, so.
Oh, you.
But don't you get an email once it's posted?
No.
No?
Yeah, check my email.
Unless you do it going.
Right? If you get an email, then everybody who
Not
gets
in that,
blacklisted.
in that black book, you sign up in the little.
No, don't you get an email when something's,
It should be connected to your email account.
It's not mine.
Mine, I get emails.
Like your mailbox.
I get emails, but I don't get emails.
You ready to go?
did you have to,
It has to connect it or something.
If you set the app,
I think it alerts you.
Only time we get an alert is for the, I think the progress.
the gun drill.
oh, the, yeah.
That's drill this
I
The active shooter drill.
I don't include those, yeah.
There's a pair
No,
of
they,
shoes
well,
or.
they have had that a couple times where they had a shooting at the mall and the person's on foot and they shut down the school.
What?
Yeah, it happens a lot of times during the day. Like someone will do something over at Roosevelt Field
Yeah, but usually they send like a text message.
and they'll send a text, but then what they'll do is they'll do a lockdown of the classes. Like I've had friends who are AP professors and during the day and they've gotten like locked in their classes for like 2 hours.
What?
Yeah.
I would have been like, bye. I gotta go.
You gotta go, sorry.
I don't care.
I don't know how well security is walking around the buildings, but everybody's locked
They
in.
well enough to give you a ticket if you park in the wrong damn
You
parking
know,
spot.
because
They'll do
God
that.
forbid, you know what I'm saying, God forbid the shooters on campus. Like until they know that it's safe, they tell everybody to stay in their rooms.
I'm gonna get in my car and drive.
Yeah, but they can't, you gotta,
They won't let you go.
you know what I'm saying, like, I don't know if they put guards at each building when that happens. So they won't let you out.
We even have that newspaper. FYI, my birthday's in March 7th. Did you bring it?
Who's yours? No, it's other. Happy birthday to you. Happy birthday to you.
What's wrong with that?
She didn't take it. I'm going to take it. Love you too.
Here, have your cake. Look at that. Oh, that's like, yay. What's on the picture?
It's just flowers.
Oh.
Nice.
Okay, you can put your cake.
Nice. What's up, mommy?
Wait, baby.
That was so nice.
Don't drop it. Don't drop the cake. Don't drop the cake. Oh, she's got it. Oh, she's got it.
What is it? Yeah, I brought, I don't know if you guys want that. I brought you like spoons.
What kind of cake is it?
Oh, you did cake?
No, that's the kind.
Oh, I don't know. I think it's chocolate. Oh, it is? Oh, what's it? I'm like, this Saturday?
I'll take the picture. There you go.
Who else wants cake?
The little man? Come here. Thank you.
Who else wants a piece?
And there goes the blood glucose levels.
It's good, BJ's is hospital.
Yeah.
Do you guys want cake? Do you guys want cake over there?
Just have this. It's good. No, I have to. Done already. You like it? Yeah. Good. I'm done.
The spirometry that you were showing, that's for what paper? For spirometry?
What do you mean, what type of spirometry?
Like, I was asking you, and you said that that's much more.
Well, it's going into other different things. I mean, yes, it's more detailed. I'm just giving you a basis.
So you're saying that would be on technically, like if I looked at my spirometry results, these numbers that you're saying would be on there?
You should be able to calculate those basic numbers from your spirometry
Or if
reading.
they're on there, I
Right.
should be able to know what they
Right.
mean.
Like sometimes what they may do is like you might be able to calculate certain numbers and then other ones, if you do subtraction, you'd be able to come up with another.
Right, but also like certain doctor's offices have some things and certain doctor's offices
Right.
don't.
I mean, that's just the basic spirometry
That's
graph.
something, so that's probably the one that like nutrition has or
Right.
whatever, and then the allergists and pulmonology, like they all have different.
Right. Because we're all testing for different things. All right. Let's get back to lecture. Thank you very much for the cake.
When's your birthday?
January.
Capricorn?
No. That was because I hate water.
That's such a weird thing.
All right. So what we're going to do now is we're going to take a look at what we call saturation curves. Remember, we had talked about saturation is the ability of oxygen, okay, to bind to hemoglobin, okay, inside your red blood cells. So one of the most important things in saturation, okay, or how much oxygen combines with hemoglobin, is the pressure of oxygen. Okay, so here we have a graph, pressure of oxygen on the bottom, and the percent saturation over here. And we can see that as the pressure of oxygen goes up, so does your saturation, percent saturation. So the higher the pressure of oxygen, the greater the saturation. So that means the greater the ability of oxygen is going to bind to hemoglobin. Okay? So when we're talking about saturation, it's your oxygen molecule's ability to bind to hemoglobin.
Wait, Professor, you said the higher the pressure.
The higher the pressure, okay, let's read the graph. As we're going, pressure, here's on the bottom, Janelle. Here's the pressure of oxygen on the bottom, PO2,
Uh-huh.
pressure of oxygen. As we increase in pressure, right? As we're increasing in pressure, what's happening to this red line? It goes up, right?
Yeah.
So that means the greater ability, okay, oxygen has to bind to hemoglobin, therefore your red blood cells become more saturated with oxygen. Now, what are some things that can affect saturation? Okay, your body's blood pH can affect the ability of your red blood cells to bind oxygen. Okay, so we have normal blood, which is the black line. So we just follow it along. Okay? Look at where they have the dash. They have a pressure of oxygen at a PO2 of 30. We follow it up to the black line. It's about a 50% saturation. Everybody see that on that black line? Okay. Now, let's change our pH. Okay? So if we go to the red line where it says low pH, 7.2, that would be becoming more what? Acidic. Good. So that's good. So if your body is becoming more acidic at that same pressure of oxygen of 30 millimeters of mercury, what would be the saturation level? About 35, right? So if your body becomes more acidic, okay, you can't bind as much oxygen inside your red blood cells.